We want to talk about the physics concept of power. Energy is the ability to do work. Work is force times distance. Power is how fast you're doing work. It's how fast you're converting energy from one type to another. If you ask me what makes you tired, you don't get tired by doing work. You get tired by generating more power. It's the difference between walking slowly up a flight of stairs and sprinting up a flight of stairs. You do the same amount of work, stairs is MGH, but you'll be tired by sprinting because of power. Power is the rate at which work is done. Anytime something is a rate, it means you're dividing by time. Power is work over time. It's the rate at which energy is transformed from one form to another. What are the units? Well, it would be a joule per second. It's a scalar. I'm going to write that again because for some reason kids forget. But power is such an important concept, we've given a joule per second a special name. Time for the terrible joke. Power is measured in watt? Yes, it is. By the way, this does give us a problem because this W is going to be appearing all over the place. You're going to be doing stuff like power equals work, don't write this down, over time, and suppose the work is 10 and the time is 2, and you're going to say 5 W. Is that 5? Which you're just going to have to look at the context to see whether it's watts or west or work. And I'm sure once or twice I've mentioned we don't have enough letters to go around in the English alphabet. It'd be nice to have a few more. If you're expending energy, it's not how much work you do that makes you feel tired. It's how fast you do the work, or honestly, how much power you generate. Power is what leads to tiredness. By the way, this is how stairs and ramps work. You expend the same amount of energy going up a ladder or going up a stairway, but the difference between going straight up a ladder and going up a stairway, the stairway lengthens the time, and because it lengthens the time, it reduces the power. You may take more time. So if we think power equals work over time, as time increases, power decreases. Work doesn't change. Hey, you figured this out if you've ever been doing manual labor. If you do it slowly, you're not huffing and puffing. If you do the same task quickly, same amount of work, you're huffing and puffing. Time in the bottom, that's what makes you tired. That's in the equation. That's what makes you tired. So a girl runs up a flight of stairs in 2.6 seconds. What's her power output in watts? So we would say this: power is work over time. If you're climbing a flight of stairs, what's the work that you're doing? Well, we could walk through an entire, it's the change in potential plus the change in kinetic. They're going at a constant speed, so the change in kinetic is 0. You know what? It's MGH divided by time. 60 kilograms, that's around most of your masses, a little bit more, a little bit less. 9.8. 3.32 divided by 2.6. 3.32 meters would be about a half flight of steps higher than this stairwell behind my room in the corner. Could you run that in 2.6 seconds? All of you could if you had to, but you'd be huffing a little bit. Oh, and if I asked you to do that 10 times in a row, you'd be giving me a pretty bad look. And by the end of that, you'd be huffing and puffing. What's the power output, Noah? That was my hint to say, maybe you want to start typing on your calculator now. Daniel, what's the power output?
7, 0.4.
7?
730.47 watts.
Is that right? I think that's a tiny bit off. I think it's 751. I contrived these numbers on purpose for part B. The imperial version of power is horsepower. What a stupid unit. We don't use horses anymore, but it's still there. 1 horsepower is 750 watts. Running up a flight and a half of big stairs, not house stairs, if you were hustling up that 2.6 seconds, you would have to be running. That's about almost exactly 1 horsepower. All of you are capable of generating 1 horsepower in bursts. If I ask you to keep doing it for a long time, Enrico, you're going to start to huff and puff and eventually stop. But all of you, most humans, even elderly humans, in an emergency, they can generate 1 horsepower. Horsepower was originally defined by James Watt. I think I told you last year, to me, he's one of the most overrated people to have a unit, especially such an important unit that all of you have heard of it, named after him. What he was a good promoter. He didn't invent the steam engine. He improved the steam engine, but he invented the horsepower because he would go to farmers and he would say to them, hey, this steam engine can do work at your farm. And the farmer would say, well, how much work could it do? And he would say, oh, 4 horsepower. What does the farmer immediately think? This does the same amount of work as what? Yeah, total garbage. It has nothing to do. It's a made up unit. I mean, first of all, horses come in different types and different styles. What, Clydesdale horse, like the big little pony? It's a nonsense unit, but it caught on so well, we still use it. Drives me cray cray. Example 2. How long would it take to lift a 5 horsepower? So how long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters high? A few notes. I would probably mentally underline the word lift. Lift tells me how will I calculate the work? It's going to be MGH. I'll file that away. They want how long. So I'm going to start out going power equals work over time. I guess I need to get the T by itself. Evelyn, where is the T right now? On the bleh. I think I could times the T to the top and at the same time divide the power down. I think time, yet another equation for time, is work over power. I also don't like my units, Daniela. I think I'm going to need to convert the power from 5 horsepower to watts. Where am I going to want horsepower in my conversion fraction? On the, yep, watts on the top, and apparently 1 horsepower is 750. You don't need to memorize that. If I do ask you to do a conversion, I'll give you the conversion factor in the question or in the line above, which we have right up there. How many watts is this motor? Sorry? 3750? That goes walking over there. So we're going to get this. The time is going to be work. How did we calculate work done in lifting? It's going to be MGH over 3750. It's going to be 500 kilograms. That's a heavy safe. That's, more than a piano. 9.8, 30 meters, all over 3750. What do you get? It works out to nice. Well, that's a fluke. 39.2 seconds. Okay. What if you need the job done faster? It's impossible with this motor. You would need to get a more powerful motor. Now, this is kind of a silly example, but if you've ever seen those big construction cranes, the skyscraper ones, they can actually calculate fairly accurately based on how much material they have to lift and how much MGH of all the material they're going to lift. They can pretty much calculate fairly accurately how long it's going to take them to lift all that building into place. Then it's just a question of the workers installing it. There's another way to think about power. Power is work over time, but work is what times what? Force times distance. So I put the force times distance right here. Can you all circle the d over t? What are the units for distance? What are the units for time? So what I've circled is meters per second. What do I measure in meters per second? We're in scalarville, so technically not velocity, but yeah, another way to calculate power is force times speed. Did I give you that one on your formula sheet? I can't remember. I used to not. Are there two versions of power on your formula sheet? I did? How should say P equals W over T. That I know. It says equals four. Wow, I'm mellowing. Okay. How do you know when to use that? They'll ask you to find the power, and you see, Captain Obvious, newtons and meters per second. Now, this works when it's a constant velocity, so the forces have to be balanced. Efficiency. Efficiency is how much bang we get for the buck. How much useful work do you get out as a fraction of how much work or energy or power you put in? It's usually expressed as a percentage. The Greek letter eta is usually used to represent efficiency. I only learned that a few years ago. I always just wrote EFF as my abbrev for efficiency. So in my answer keys, you might see that I still did that because I made some of these answer keys up several years ago. But the Greek letter eta, it looks like a lowercase n with kind of a droopy tail on the right. So how do I calculate power? Well, sorry, efficiency. Efficiency is always power out divided by power in, or work out divided by work in, or energy out divided by energy in, and then times 100 to make it a percent. Yep. And then I gave you a better way to remember that. I don't memorize that. Here's what I know for efficiency. Efficiency is always going to be the smaller number divided by the bigger number. Because you cannot be more than 100% efficient. And in fact, you can't be 100% efficient except in some very bizarre physics situations like superconductors and things. But I'm going to say, as a rule, you can't be 100% efficient either. You always lose something in the transfer. Always. So I wrote here, efficiency is always less than 100% unless you plan on winning a Nobel Prize. You can't. Another word for more than 100% efficiency, if you want to sound poetic, we say efficiency is over unity, because unity is 1, 100% is 1 as a decimal. If you have somehow achieved over unity, that's what we call a perpetual motion machine. You may have heard the term. There are thousands of people sending in ideas for perpetual motion machines all the time. I read once that I think the US Patent Office, they just have a stock form. Dear Mr. blah, blah, blah. Line blah, blah, blah. That's the line in their patent that doesn't work. That's not going to be a perpetual motion machine. Send it. They don't try and do a full answer anymore. You'll find, I was going to say dozens, probably hundreds, maybe thousands of quack videos on YouTube that will claim to have perpetual motion machines. Can't do it. Sorry, you can't do it. Sorry, you can't do it. If you could somehow get free energy, more energy out than you put in, if you did invent a perpetual motion machine, within about 5 years, you could buy Amazon and Bill Gates and Warren Buffett. You'd be the richest person on earth. Because if you give us free energy, even with our current level of technology, just with that, we can engineer our way out of most of the world's problems pretty easily. But we can't. Typical household light bulb transforms energy at the rate of 60 watts. How many of you still have the incandescent bulbs at home? The big screw-in ones that get really, really hot? Or have you all moved to LED? See, we're in that transition. I'm probably going to have to remove this paragraph in probably 2 or 3 years, because it says most of the electrical energy is transformed into heat instead of light. That's for the old incandescent bulbs, the ones that when you turn them on, they get so hot that you'll burn yourself when you touch them. Only so you get about 57 watts of heat, and only about 3 watts of light are produced by the lamp. An incandescent light bulb is only about 5% efficient. LEDs, much more efficient, and you may have noticed if an LED is on, it gets warm, doesn't get hot. You could probably unscrew it after it's been on for a while without burning your fingers. Some of you may have had as a kid a toy called an Easy Bake Oven. All that was a glorified, I think it was a 200-watt light bulb in there, generating a lot of heat, very inefficient, but you could cook things. Well, you could cook mushy brownies, and what's better than mushy brownies, right? I'm seeing a few of you. Oh, yeah. Okay. Sorry? Oh, yeah. A kettle might transform electrical energy into heat at a rate of 1500 watts. Most appliances, somewhere printed on the appliance, it's supposed to have the wattage that tells you how many joules of energy per second it's transforming for a kettle into heat, for other things into other things. Example 3, a 250 kilogram mass is lifted at a constant speed. I probably underline the phrase constant speed for a distance of 12.5 meters. Okay. A says find the work done. You know what? I would probably underline the word lifted. Callie, if I want to find the work done in lifting, how do I figure that out? Yeah. It's going to be 250 times 9.8 times 12.5. Which is what? Should be fairly big. 250 kilogram mass is pretty heavy. 12.5 meters, about 4.5, 5 stories. So, okay. What'd you get? 306,000. That's not something that most of you could do. You could put out 300,000 joules, but not in this situation. Let's try that again. That seemed a little large to me. Read me the digits. 3. Okay. Like that? Is that right? Okay. Note to self. Don't go to Callie again. Okay. Okay, redeem yourself, Callie. Then what does B want me to find? My first thought would be, well, power is work over time. Do you see a time in seconds anywhere? Now, I might be able to calculate time, but I think what I would do, especially since they included the phrase constant speed, I might pivot to my second definition of power, which was force times speed. And then I would say, well, did they give me a speed? Ah, I'm on to something here. So the speed is going to be 2. What's the force we're lifting? What's the force we're lifting? Yeah, I think it's going to be the same size as mg. If you do your free body diagram, it's moving at a constant speed. Mg is down, but whatever force you're lifting with would have to be the same size because it does say constant speed. So I'm not saying the force is constant, is mg. I'm saying it's the same size as mg. So it's going to be, what, 250 times 9.8 times 2. I don't even trust Callie. I better do this one in my head. It's going to be 500. Is it 4,900 units? Power is measured in watts. Now, let's suppose the motor used 10 kilowatts of electrical power. Find its efficiency. Efficiency is going to be smaller number divided by the bigger number. Am I going to do, and the units have to match. The fact that they gave me 10 kilowatts, which is the same as 10,000 watts, I think I'm going to do this in watts, not in joules. And I think that's the bigger number. The smaller number is 4,900 watts. I don't even need a calculator for that, Daniel. I'm pretty sure. Oh, and then times by 100 to make it a percent. 49%. Yes. The fact that we got 49%, I would be. Oh, it is an electrical power. It says electrical. That's really bad for an electrical motor. Electrical motors are usually much more efficient than that.
Oh,
What was your question? 10 kilowatts. Kilo. Example 4. A mass of 100 kilogram is pushed along the floor at a constant speed. Again, I'd probably mentally underline constant speed. If the coefficient of kinetic friction is 0.25, that phrase, I bet you I'm drawing a free body diagram. What's the power output? Okay, we can do this. Noor, what do they want me to find? And the fact that they gave me a speed, I'm going to guess I'm going to use force times speed, not work over time. Also, I don't see a time in seconds anywhere. I might be able to calculate, but I don't see that. Okay. Which force? I guess it's going to be F applied. Pushing. I don't know F applied. This is a job for a free body diagram. Let's do that over here. What are the forces acting on this object? Noor, get the obvious one. What else? Yep. Then we have F applied. What else? This can't be it. Bigger, smaller, or the same size as F applied, and how do I know? So if it's smaller, then it wouldn't be moving at a constant speed.
same size.
Has to be the same size because constant speed means A is equal to what exactly as a number, which means forces must be. I'm looking for a word that starts with letter B. Yeah. So let's go back to what we said. Power is F applied times speed. I don't know F applied. Oh, but look. I know another force the same size as F applied. Which force? Has to be because of constant speed. If it wasn't constant speed, this question would be unsolvable. But power is going to be the force of friction times speed. Friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? And then the V is still there. Yeah, the power here, I can figure it out with this information. It's going to be F applied times speed. I don't know F applied. It's going to be friction times speed. I don't know normal force. I have to do some hopscotching, but yeah, I can get this. It's going to be, what's mu? I don't know what's mu. 0.25 times 100 times 9.8 times 2. Do that one on your head. You know what? I might be able to actually. 0.25 times 2, that's going to be 0.25, 25. What's a clever way to multiply by 25? Times by 100 and then divide by 4. 220, no, I'm 200, what do you get? 490. I forgot to carry an extra 2 in there. Watts. Okay. I think I divided by 2 one extra time. I was trying to say 245. Silly. Got the right answer? Oh, you didn't get the right answer. You got the wrong answer. I think that's really what we mean. Okay. I'm going to make an executive decision here. This lawnmower question is cool, but we've done so many vectors and components. I'm going to say meh, and I'm going to say meh. So I'm going to jump to example 8, which will finish off the unit. That's why I said meh. Oh, where's example 7? I must have nuked it. On a stair climber at the gym, a 75 kilogram person lifts their center of mass up 22 centimeters. Nice try, Mr. Dueck. 0.22 meters with each step. If they take 360 steps in 6 minutes, nice try, Mr. Dueck. 6 minutes, how many seconds? 360? Okay. And their muscles are 18% efficient. Then find, ooh, okay. Matt, what does A want me to find? Well, read it to me. What's that physics speak for? Yeah, power. The rate at which you're doing work is power. So my first thought would be, you know what? I see a time. I'm going to go power equals work over time. And I make a little note here, Matt. Lifts. How do I calculate the work this person is doing? If they're, yep, it's going to be mgh over time. What's M? 75. G? 9.8. What's H? I'm going to give you a hint. It's not 0.22. Not 0.22. How many steps are they taking? Yeah, they're raising themselves over and over on this stair climber. I'm just going to go 360 times 0.22, and you're going to see why in a second, Matt, because what's time? And it turns out by a wonderful fluke, those will cancel out. You don't have to, but yay. Yeah, it's going to be whatever 75 times 9.8 times 0.22 is. Or whatever 75 times 9.8 times 360 times 0.22 divided by 360 is. What do you get? 1/6 to 1.7? Okay. Hours measured in watts. That's how much energy they put out, but their body actually used up more energy than that. So it says if their muscles are 18% efficient, then find the rate at which they used food energy. This would be the rate at which they were burning calories. This is why, by the way, any fitness machines that you've been on that claim to tell you how many calories you've burned are bogus. Even if you input your weight, which only the newer ones do, most of the older ones don't do that, they're bogus. I'll show you what I mean. What does this want us to find? Well, we're going to use efficiency. So I'm going to write down efficiency equals, and it's out divided by in. That 161.7, is that the power we got out, or is that the power we put in? And this is why it's a bit tricky. This is why I actually think of this as, I know the smaller number is going to be on top. Did this person generate more power than that 161.7 doing the actual exercise? Was their energy going to other areas than just stair climbing? Were they giving off heat? You know what? I think this is the power out, the 161.7. I think we want to get this number by itself. Where is that number right now, Matt? On the, ugh. But I think I can multiply it to the top. And I think I'll get out divided by the efficiency. It's going to be 161.7 divided by, not 18. What do you have to turn that 18 into before you do math with it? 0.18. This is actually how much power, how much energy per second this person was burning. What do you get? I agree. Power is measured in watt. Power is measured in watt. Everybody? Watts. What was it? 898? How long were they working for? The question told me. If I wanted to find out how much energy they burned, times by, because that's how much joules per second, that's what power is. That's how much energy they burn. And machines can't calculate that unless they know your metabolic efficiency. Okay. It's also why, by the way, uh, if you're in really bad shape, your body is less efficient. You'll burn energy better. It's the exercise has a better effect on you than if you're in really good shape. Once you're in really good shape, it's hard to get into really, really good shape. If you're in really bad shape, although it's more painful and you find it tougher emotionally and you're huffing and puffing, the curve of getting into okay shape is generally shorter. It's your homework. Yeah, you can talk. Yeah, you can write. I'm not going to assign any questions from lesson 4. I want to give you as much time as possible. I wanted to give you 30 minutes. You can start working on the ultimate review. There's also lesson 5, which is tomorrow, will not have any homework attached to it. It's a topic I could put anywhere. It's clever graphing tricks that you can use to interpret graphs in physics or in calculus for those of you that are in calculus, or in chemistry for those of you that are in chemistry. It's going to be why would I memorize stuff if I can just derive things by being a bit clever? So there won't be homework there. So your homework now is to start whittling away at the ultimate review.